In order to understand the Jacobian method, we shall start with something that is already familiar. X is a random variable with density little fx and CDF capital Fx. Now we are given a function h which is an increasing bijection, strictly increasing bijection. So h inverse exists and we assume that h inverse is differentiable. So this h is given to us, x is given to us. Now we shall apply this h to that x and as a result get a new random variable y. We are interested in finding out the density of y. Of course, the natural way to start is to first construct a CDF, the CDF of y, because it is strictly increasing. That will be easy to do. Let's call it gy. So by definition it is probability y less than or equal to little y, which is probability hx less than or equal to y, because y is hx. Now we are going to use the fact that h is a bijection, so we are going to take this h on that side. So we are basically applying h inverse to both sides. And here you have to be careful. H is strictly increasing, which means h inverse is also strictly increasing. Don't think that h inverse is strictly decreasing. So when I apply h inverse to both sides, the inequality remains unaltered and we get x less than or equal to h inverse of y. Now I have assumed that x has CDF capital Fx, so this is nothing but capital F evaluated at h inverse y. Now our aim was to obtain density of y, so we plan to differentiate this and we shall use the chain rule because h inverse was assumed to be differentiable. I first differentiate this capital F to get little f and I leave whatever was inside unaltered. Then I differentiate h inverse, so I write the derivative of h inverse y. So the density of y is given by this particular expression involving density of x and inverse of the transforming function. Now this very important formula was obtained under the assumption that h was strictly increasing bijection. Of course, we cannot drop the bijection assumption, otherwise we cannot use this h inverse. But if we make it strictly decreasing, then also essentially the same argument will work, inequalities will just reverse. In this case, h inverse will also be strictly decreasing, so its derivative will be negative. Obviously, density cannot be negative. So if you just carry out the steps, you will find that you will have a minus sign before it. So this is negative and that negative will cancel off and it will still give you this thing. So for any monotone bijection, this is the general form. If I put absolute value, it will work for both strictly increasing and strictly decreasing. Now I claim that actually this formula holds for any bijection h as long as h inverse is differentiable. Remember, we are working from R to R. So if you have a bijection and its inverse is differentiable, which means your h inverse is actually continuous, it's a function from R to R, so h must also be continuous. So if a function is continuous from R to R and is a bijection, it has to be either strictly increasing or it has to be either strictly decreasing. Because if it increases and then decreases, it ceases to be a bijection because the same value is taken in at least two places. So if I just say it is a bijection with differentiable h inverse, that's enough for my purpose. I can really forget about the monotonicity which will now follow as a consequence. So we have got this useful result that for any bijection h from R to R with differentiable inverse, density of the transformed random variable is given by this formula. Now remember this formula as the Jacobian formula for dimension 1. It's a single dimension, R to R. In fact, this is what is called the Jacobian. Now before we go into higher dimensions, let's get used to it by doing an exercise. In this exercise, x has this particular density where c is a suitable constant such that the total integral becomes 1. You don't have to worry about c, just keep the answer in terms of c. Your job is to find the density of y equal to root x. Now you might feel uncomfortable because here the role of hx is being played by root x, which is not defined over entire R, because if x is negative then it will not work, but don't worry. In our case x always takes positive values, so the result that we did can be applied just restricted over the positive half. You can still apply the same formula.